Chapter 4, problem number 40. A 6 kilogram box is sliding across the horizontal floor of an elevator. The coefficient of kinetic friction between the box and the floor is 0.360. Determine the kinetic frictional force that acts on the box when the elevator is stationary and B, accelerating upward with an acceleration whose magnitude is 1.20 meters per second squared, and accelerating downward with an acceleration whose magnitude is 1.20 meters per second squared. Okay, so let's write down the given information. So we have a 6 kilogram box. Coefficient of kinetic friction is 0.360. And they want to know what the kinetic frictional force is when the elevator is stationary. So that means that the acceleration of the elevator is 0. So part A, what is the force of kinetic friction? Well, kinetic friction only occurs when there is relative motion between two surfaces in contact. So the box is sliding, the elevator is stationary, so the equation Fk is equal to mu k times the normal force becomes mu k times the mass of the box times the acceleration due to gravity. So we take 0.360, multiply that by 6 kilograms, multiply that by 10 meters per second squared, and that would be the force of kinetic friction between the box and the floor of the elevator if it's being slid at a constant speed when the elevator is stationary. So we have 21.6 newtons. Now it gets really interesting. The elevator is now accelerating upward with an acceleration of 1.20 meters per second squared. Okay, so upward. And they want to know, again, what is the kinetic frictional force? So we're looking for Fk prime. So the equation for the kinetic frictional force is mu k times the normal force. Now normal force can also be thought of as apparent weight. So if you put yourselves in the shoes of 6 kilogram box, what is the apparent weight of the 6 kilogram box? So we're going to use Newton's second law to figure this out. Okay, can you still see that? Part B. There we go. All right, so here's the elevator. Well, the box in the elevator. We're going to look for the apparent weight, which we're calling Fn, and it's Fn prime, because it's different than previous. The weight of the box is mg. Same as before. This is larger than that because we need a net force upward to allow the elevator to accelerate upward. So using Newton's second law, we have that the normal force, prime, Fn prime, minus the weight, mg, is equal to ma. So solving for Fn prime, we get mg plus ma, or m times the quantity g plus a. So that's the normal force on the box. Now, since that's what the box feels it weighs, okay, that is what we insert into here, because that's the upward electric force on the box. So Fk then is equal to mu k times the normal force prime. So we have 0.360 times this value here. So let's see, we have the mass, 6 kilograms. G is 10 meters per second squared. Notice it's just the magnitude. And then plus the acceleration with direction, 1.20 meters per second squared. Okay, so that goes here. So let's see what we get. Let me figure this out, and then I'll multiply it by 0.360. So I'm getting 24.2 newtons, which you notice is more than it was previously. Okay, that brings us to the next part. Now the elevator is accelerating downward. So they want to know what the force of kinetic friction is, and its downward acceleration is 1.20 meters per second squared. So I'm just going to change this to part C, make this negative, and we have the same equation here. Now the normal force is going to be less than the weight, so that we can get an acceleration downward, and we're looking for the normal force, so that then we can multiply that by mu k to get the new force of kinetic friction. Now this should be less, right, because the normal force is going to be less. So we have Fn prime minus mg, that's the net force, is equal to ma. So Fn prime is equal to mg plus ma, or m times the quantity g plus a. But now acceleration is downward, so we have minus 1.20 meters per second squared. Let's see what we get for the force of kinetic friction. (19 newtons), much less than what it was previously.